every sunrise feels familiar. The same star appears above the horizon, flooding the world with light and warming a planet nearly 150 million kilometers away. We know its age, its size, and the source of its power. We can split its light into a spectrum, listen to vibrations moving through its interior, and send spacecraft close enough to pass through its outer atmosphere. And yet, the nearest star to Earth is still filled with mysteries. The Sun is a sphere of plasma more than 1 million kilometers wide. Deep inside its core, immense pressure forces hydrogen nuclei together, creating helium and releasing energy through nuclear fusion. But the energy born there does not travel straight into space. Photons are absorbed and re-emitted countless times as they struggle through the dense solar interior. A journey that begins at nearly the speed of light may take tens of thousands of years before reaching the visible surface. From there, sunlight needs only 8 minutes to reach Earth. This broad picture is well understood. The unanswered questions begin when we look more closely. Above the Sun's visible surface lies an atmosphere called the corona. It is a pale, ghostly halo normally hidden by the brilliance below, but revealed during a total solar eclipse. The surface of the Sun is about 5,500 degrees Celsius. The corona can exceed 1 million degrees. This seems to defy intuition. As we move away from a fire, we expect the temperature to fall. But above the Sun, the thin outer atmosphere becomes hundreds of times hotter than the surface beneath it. Something is carrying enormous amounts of energy upward. Magnetic fields are almost certainly responsible. The boiling motion of plasma below the surface twists, stretches, and tangles magnetic field lines. When those fields suddenly rearrange, they can release energy in countless small eruptions. Some scientists suspect that a constant storm of tiny events, called nanoflares, heats the corona. Another possibility involves waves traveling through the solar atmosphere. These waves may transport energy away from the surface and deposit it high above. Both processes have been observed. Both may contribute. But exactly how the energy is transferred, where it is released, and which mechanism dominates remain open questions. The corona does not stay bound to the Sun. It expands outward as the solar wind, a continuous flow of charged particles that moves through the entire solar system. It sweeps past planets, shapes comet tails, and creates a vast bubble around the Sun called the heliosphere. Spacecraft have measured this wind for decades, but scientists are still working to explain how particles escape the Sun's gravity and accelerate to such extraordinary speeds. The slow solar wind presents an especially difficult puzzle. It appears to emerge from complex regions where magnetic fields open, close, and reconnect. Its precise origins shift across the Sun and change over time. NASA's Parker Solar Probe has flown closer to the Sun than any previous spacecraft. It has crossed into the corona, sampled the solar wind near its birthplace, and discovered sharp reversals in the magnetic field known as switchbacks. These sudden bends may help transfer energy into the solar wind, but what creates them and how important they are to the wind's acceleration is still being investigated. The Sun also follows a rhythm that we cannot fully explain. Roughly every 11 years, its surface changes from relatively calm to increasingly violent. Sunspots multiply, solar flares become more common. Vast eruptions called coronal mass ejections hurl billions of tons of plasma into space. Then the activity fades and the cycle begins again. This behavior is driven by a solar dynamo, the motion of electrically conducting plasma that generates and reshapes the sun's magnetic field. During each cycle, the magnetic poles eventually reverse. North becomes south and south becomes north. We understand many of the ingredients: rotation, convection, flowing plasma, and magnetic fields. But we still cannot build a complete model that reliably predicts the strength and timing of every solar cycle. Some cycles are weak, others are intense. Sunspots can nearly disappear for decades, as they did during the Maunder minimum in the 17th century. Why the dynamo changes so dramatically and whether a prolonged quiet period can be predicted remains uncertain. This is more than an abstract problem. Solar eruptions can reach Earth. When a coronal mass ejection strikes our planet's magnetic field, it can produce brilliant auroras. A powerful event can also disturb satellites, interfere with radio communication, alter navigation signals, and drive electrical currents through power grids. Scientists can often identify active regions where eruptions are likely. They can watch magnetic fields grow tangled and unstable. Once an eruption occurs, spacecraft can track its movement toward Earth. But predicting the exact moment a solar flare will happen, or whether an active region will erupt at all, is much harder. Even when a coronal mass ejection is on its way, its effect depends on the orientation of the magnetic field carried inside it. A field aligned in the wrong direction can connect strongly with Earth's magnetosphere and produce a severe geomagnetic storm. That crucial orientation can be difficult to know until the eruption is already close. The sun also hides mysteries in its chemistry. Astronomers once thought they had a consistent picture of the amounts of elements such as carbon, nitrogen, and oxygen inside it. Then improved models of the solar atmosphere led to lower estimates for several of those elements. The new measurements created a conflict. Models built with the revised abundances no longer agree as well with helioseismology, the study of sound waves traveling through the sun. Those waves reveal the structure of the solar interior with remarkable precision. Either the measurements, the models, or parts of our understanding of the sun's interior still need to change. This is known as the solar abundance problem, and despite years of work, it has not completely disappeared. Each mystery is connected to the others. The hidden motion of plasma creates magnetic fields. Those fields produce sunspots and eruptions. They carry energy into the corona, shape the solar wind, and determine how the sun affects every world around it. To understand the sun, we must follow a chain of events from deep inside a star to the edge of the solar system. New observatories are revealing that chain in unprecedented detail. Telescopes on Earth resolve structures on the solar surface only tens of kilometers across. Spacecraft watch the poles, image the corona, and taste particles flowing directly from the sun. Every discovery narrows the possibilities. It also exposes new complexity. The sun is not a simple ball of fire. It is a moving ocean of charged matter, shaped by forces that twist across scales, from microscopic interactions between particles to magnetic structures larger than Earth. It has shone for billions of years and made nearly all life on our planet possible. Still, we cannot fully explain why its atmosphere is so hot, how its wind is accelerated, what controls its magnetic cycle, or exactly when its next violent eruption will occur. The most studied star in the universe remains in many ways unknown, and every morning those mysteries rise with it.